right, guys, welcome to another episode of Cuda Education. Today we want to talk about um, shader binding table and data that is included in the data region for the shader binding table. So we have our shader binding table and we want to basically include some data as part of the SBT, shader binding table, SBT. We want to include some data in the shader binding table and then have it accessible in the shaders. So remember the shaders now, these things live on the GPU, and we want to be able to access information in the shaders by way of the data region in the shader binding table. This is the ray tracing SBT data application, ray tracing SBT data.cpp application. It is another application from Sascha Willems's Vulkan examples solution. So he has a bunch of examples. And here we're trying to tackle the idea of the shader binding table, having a data region, and then we could pass information into the shaders via that route. Again, this is one of the things where, from where I stand in my journey in Vulkan, I can't fully appreciate the value of this, but I'm sure it will come in handy in one way or the other. So that's what this video is about. It's a lot of stuff to cover, but I hope it to be a short video. All right, so let's just, I think the first thing we need to do is, let's just run the application. So, okay, I have that. So let's just run the application. So, one second. All right, sorry guys, I had to recompile my shader because I was messing around with shaders, of course. So let us run the application and we get this bad boy. Now, notice that first of all, we have a rendered triangle, right? We have a rendered triangle, and that rendered triangle is red. All right. Second thing to notice is that we have a checkerboard pattern, right? And we will discuss that. We have a checkerboard pattern that sort of overlays the triangle. So we do have our triangle, and I could actually move around the triangle. But we have a checkerboard pattern overlaying the triangle, okay? Checkerboard with white and gray. All right, so you guys get that. We have a checkerboard pattern, we have our triangle, we're good. Also, what you guys need to understand is that we have a black background in the application. So we actually have a background, and then we have this checkerboard pattern, and of course the triangle inside of it that is part of the mix, okay? But we do need to just kind of appreciate that we have a black background behind, or basically surrounding, we have a background, and then we have the checkerboard pattern, and then we have the red triangle. All right, so let's just set everything in context from there. All right, so we could exit that now. All right, so the main heart of this application is that we have create shader binding table function, and then we have we allocate space for the handle, which is like lambda function pointers to call in the ray tracing pipeline, as well as data to pass to those functions. which act as the variables being captured by those lambda functions. Basically, you know, what I gather from this, and this is sort of an initial video. I'll probably revisit this at a later date with more information. So this is an initial video. But basically, we we have this extra space here, handle size 3, size of float. So, you know, we're doing what we normally do, but we have this extra space here, shader group base alignment, and we have this extra space here, and we are creating buffers for each of the entries. So we have regen shader binding table, miss shader binding table, and hit shader binding table. But we're creating buffers for each shader. Okay. We have our flags, and we are creating entries, buffer entries for each one of them. We do a map copy handles, we do a map, and then we mem copy over shader handle and storage data. So we have handle size, we have handle size plus handle, we have shader storage, shader handle storage data. We have shader handle storage data plus handle aligned, handle size aligned, and we have shader handle storage dot data plus handle size aligned times 2. So again, this is memory operations where we're trying to basically you know, in the data region, we're trying to basically slot in specific, you know, regions for specific stuff. So we have for the regen, the miss, and the hits. Okay. Copy over regen record data. So it's a vec3. We have our colors here. So this is the regen record. We have gray here. We have white here. This is gray. The miss is white, and then I guess the hit is red. So gray, white, and red. So we have gray, white, and red. Okay. So this is all memory operations. I'm sure the flags are important. So memory property, host visible, and host coherent. That just means that memory is visible between the GPU and the CPU. And then shader binding table bit KHR and VK buffer usage shader device bit. I might do another video that kind of gets into these flags in more depth. But for now, what I want to impart to you guys is that you know, we are on sort of in our CPU code, right? In our code, we are making allocations for you know, for these variables, right? The red color, the white color, the black color, the gray color, the white color, and the red color. We're making allocations for them on the you know, in the buffer, right? So it's not just, we're not just having a shader binding table with the shader groups and all that stuff. We actually have now a data region where we could put in information for the different you know, for the different variables that we're trying to pass in. Now, one thing that is important to understand is that each shader, it can only access its own its own variable. And this was something a little bit confusing to me, because when you dive into the different shaders, right? All the shaders have this particular thing here. It has this, and we'll get into it. Just be patient. We'll get into it. But all of the shaders has this thing right here. Shader record ext, SBT, and it has float R, float G, and float B. And it's like the exact same thing. So it's in here. This is the hit shader. This is the miss shader. And this is the regen shader. So they all have this particular statement, the exact same statement in each one of them. And I'm like, well, what's the difference? I mean, how is it in the hit shader it resolves to a different color from the mist shader and from the regen shader if it's the exact same thing? And there is a sort of everything is shoehorned into its own particular record. Now, how it exactly does that, and why that is the case, I will have to investigate that piece at a later date. I'll probably do it in another video, right? But we're mapping these variables now into each of the respectable shaders, right? So even though we're referencing the same thing, it resolves to different values based on, what we put in here, okay? So this piece is really create the shader binding table that binds the programs and top level acceleration structure. In this example, we embed data in each record that can be read by the device during ray tracing. In this example, we embed data in each record that can be read by the device during ray tracing. So this device mentioned, we're talking about, can be read by the GPU. So remember, shaders live on the GPU. So that can be read by the device during ray tracing. So we're creating the shader binding table. This is source code. This is C++ side. But remember, we have our host coherent and our host visible. So the memory that we're using is being shared between the CPU and the GPU, right? So they both can see this memory. So the layout is here. We have our regen and we have our regen data. We have our handle, mishandle, and our miss data. We have our hit handle and our hit data. I kind of need to put a little bit more energy into figuring out how these barriers are enforced. So how, when I do this here and I do this here, that it knows that we are talking about different things, even though it's the same code and the same names and everything. How do we know that it's different? It's different colors. So I might have to put some more energy into that piece. But as far as we're concerned right now, we make sure we do our memory allocations properly. This guy, I think, is the big thing. Because it's basically saying, listen, we're doing our regular shader binding table stuff, but we also need three extra slots, because each one of these is a slot, right? Vec3, right? But again, this is my initial video. Just be patient, we'll get to that stuff. So we have our source code set up. We're making sure that the the regen, miss, and hit shader is being copied in. So we have that into our data region. And then let's do the easiest one first. So we have our ray tracing extension. We have payload in ext hit value. We already know about this hit value thing, right? But the big thing is this layout shader record ext SBT, and we have our RG and B here. So this is where the information is passed into our into the shader, right? So shader record ext. So this is where it's passed in, and then upon the hits, update the hit value to the hit record SBT data associated with this. So it's a miss record. So this is going to resolve to white, right? And we could see in our application that all of the misses resolve to white, right? So all the misses resolve to white, all the hits resolve to something else, but the misses resolve to white. So we're clear on that, right? The misses resolve to white. All right. And this is here we're passing in our record from the shader binding table, RGB. So this guy here, right? And we know it's 111, so this is white. All right. Let us go to the hit. So for the hit, similar things. We have our hit value, which we've done that before. This is just the barycentric coordinate stuff, which we're not really using, but you guys know now from literally my previous video, the one next to this one, that this is the barycentric coordinates for the hit, right? So every time you have a hit shader, you generally can get the barycentric coordinates for the actual hit, right? Where did it hit, right? So that's what this stuff is. But again, we have our construct here, RGB, and we're getting in information from the data region of the shader binding table, right? It's the exact same piece of code, but of course it resolves to, because it's the hit, it resolves to red. So geometry ID, region with this geometry ID. So we know that this resolves to red, okay? Because of this piece right here, all right? And of course our friends down here, this is the hit thing, so we know this resolves to red, right? So we get our red here. Now let us tackle the regen. So with the regen, we get, we get the camera system, we get top level accelerator, all that stuff. We have our hit value. Again, we have our data from the shader binding table, right? We have, we have our RGB for the regen. So that's this guy here. And we know that resolves to gray, right? Halfway between what, white and black, gray, right? Okay. This is camera related stuff right here. We know we've seen Tmin and Tmax. That just means like how far are you going to count stuff, when the ray shoots, how far are you gonna, we're not gonna start recording immediately because we don't want to self-hit. We don't want to, the apparatus or the camera or the lens or whatever, we don't want to self-hit. So we have a little space before we start counting hits. And then how far into the world are we counting hits? This is what this 1,000 is, right? Or 10,000. So Tmin and Tmax. We've discussed this before in previous videos, right? So we know about this stuff. All right. Use border to demonstrate regen record. All right. The first thing that we need to understand is that this part right here is related to the checkerboard. Okay, so this region right here is related to the checkerboard. So this region right here is related to the checkerboard. Okay, so this is the checkerboard stuff, right? If you want to zoom out to the triangle, all of this is the checkerboard. Okay, So this is the checkerboard stuff, right? Even in around the triangle, you still see the checkerboard, right? This is the checkerboard logic, okay? So we have our checkerboard logic here. And then this is the if use border to demonstrate RayGen record data. So this is you know, this whole piece right here, mainly this part is where we get our border, right? So the black. So remember I said that around everything is this black border. That's what this guy is down here, okay? But I just felt it important to show that for now, right? So this is the black, all right? So within our checkerboard region though, so let's focus more now on the checkerboard stuff. Here, so if we have a hit, generate a checkerboard to trace out rays or use the hit record data. So what happens is that apparently we're only, you see the regions where there's white or the regions where there's red. That's the only places that we're actually ray tracing. We're actually shooting rays where you don't have the gray. So all of the regions where you don't have the gray, we're actually shooting pixels into the scene, and we're trying to see what happens. So here in this one, we shoot pixels into the scene and it's a miss, which is why it's white. Here we shoot pixels into the scene and it's a hit. It hits the triangle. That's why it's red. So we have white for a miss and red for a hit. White for a miss, red for a hit. For all the other checkerboard parts where you see gray, and even around where the triangle is, you still see gray, it's consistent, that is where we decide that we're not going to shoot a ray. So notice that you have the trace ray ext here. This function is what shoots a ray. And notice that in the else logic, so we have an if, certain things, else. Notice that in the else branch, we don't shoot a ray. So there's no trace ray ext in the else branch of this code. Remember guys, this is the checkerboard region. This is the checkerboard region. Notice that the checkerboard region is only here. Everything else outside of the checkerboard region is black. And that's what this guy down here is. It's the black, right? So we have our checkerboard region here. And then here, the reason why I was kind of confused as to why this was the way it is, and I'm like, what is all this trying to say? But the reason why he does this, is because he wants to demonstrate that for the RayGen region, the value for the RayGen region of this thing is set the hit value to the RayGen SBT. So basically for this piece of our this location of our application, don't bother worrying about what the mist shader color is. Don't bother worrying about what the hit shader color is. Just give me the color that was associated with the RayGen payload, right? Or what the data was for the RayGen. So we did the miss color and we did the hit color. But we want to also show what is the RayGen color. So in order for him to show what the RayGen color is, all he does is say, listen, don't even bother shooting rays for these sections, for these gray sections. Don't even bother shooting rays. Just give me, for this region here of our application, just give me the color that the RayGen section has. So here, the RayGen section has RGB, which is the RayGen section, which is gray, right? So That's what that is. Now, let me go out on a limb. Let me go out on a limb. And I'm going to change the value of the, I'm going to change the value of the regen region. I'm going to change the color that we see for the mist pieces, right? So the mist pieces, we're not even shooting array. We're just displaying what the regen region has. Now, there's a bonus in doing it this way because we are doing in our source code and, you know, we're doing the data region of the shader binding table. I don't need to compile anything. Remember, guys, if I start tinkering with stuff here, I have to recompile, but here I don't. So let's see if I, well, the color changes, but the color changes to something different, but I don't. Is it gonna change again? Is why I'm sort of hesitant. Is it gonna change again? Because it kind of acts funny a certain way. Okay, all right. So it changes again. All right. So we updated the color for the regen record, and we see that we have now a different color for the parts where we're not. We're just returning whatever the regen shader had for these regions, right? I know it's kind of like counterintuitive because we're naming stuff regen, but we're actually not. We're not literally like generating arrays. We're not generating array for that region. We're just basically displaying whatever the regen shader has for that region, right? So you see every time I change the color, every time I change the color, I get, I get a different, and I don't have to recompile my shader. I don't have to get into SPIR-V and all of that. I basically just, I basically just do it from the source code, right? I mean, obviously you build and then you run, but so we see that the colors change. Right, so then we go back to what we had before, and we see that we get back our gray, right? We could also do it for the hit. But I'm not gonna do it. I don't. Why does it have this weird? I don't like this weird stuff. But anyway, let's just change this to 1. So now we get a yellow. We get a, because that's a hit record, right? If we change this to 1, no, we don't even get a triangle. The triangle is still there. It's just that it matches with the mish. It matches with the mish shader. So April Fools on you. Right. So we get our triangle, right? And then we could also do it for. We could also do it for the miss record, right? So if we do it for the miss record, we get our yellows here, okay? Right, so when we start messing around with the miss record, we get that stuff, right? Let's make sure I put things back to where it was, right? So we're back to where it was. Okay, so you know, this is the shader binding table data region, and we are messing around with the records that go into it. Um, I will suggest, guys, that you spend time figuring out exactly the memory operations. It's something. It's not my favorite part of Vulkan, but it's very, 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 very important to really understand what's going on with the buffer regions, the flags, VK buffer usage, shader binding table bits, KHR, all of that stuff, shader device address, all of that stuff, memory operations. It's very important, but that's what this guy is doing. So I don't even, for here, for the black, for the blackout side of everything that's going on, he just manually puts a color. I've tried changing this too, but you know, it gets a little messy, but he just manually puts in a color. So that's not really part of the example. And then of course, after everything is said and done and set up, we actually have to record everything in an image and display it on the swap chain. So we'll record all that we have done, all the shenanigans that we have done. We record it here, and we put it back so that it can be displayed into the swap chain. So it can go into the swap chain and then eventually make its way to the presentation, which is what we see on our screen. I could actually run a little joke for you, and basically I have to recompile because now I'm doing the shader. If we don't record back to the image, can you guess what will happen? Notice that for the other shaders, we don't have that image logic, right? But for the raygen, we have to say, okay, we shot rays into a scene, a bunch of things happened. Now record what happened, the results of all that happened, and push it back to the scene. But you're going to see that if we don't record, basically what we get is a blank screen. Right? And that makes sense. We get a blank screen because, and we get a blank screen because we're not recording any images back. We're not recording any images. We're not recording anything, you know, back to the into the swap chain, and then nothing it presents. Let me make sure that I put things back the way they were, because I don't want to be disoriented the next time around. But yeah, the big thing that we kind of need to really investigate is the memory operations. It's really, really important. So now you know, guys, that you can pass data into shaders, pass data into your device operations and stuff through the shader binding table data region. Okay. And I believe that I think I'm good now. So let me just make sure that everything is back to the way it was. We have our grays, which no rays are being shot. We have our misses, which resolve to white. We have our hits, which resolve to red. And then outside of it all, we have our black. And you guys know exactly how and why this thing happens the way it does. Okay? So we learned something today. View Solution Explorer, right? So we have closest hit, miss, and raygen. GLSL is what we're running with. So we have done ray tracing basic. I think we did callable, but I'll do it over again. Ray tracing basic, callable, ray tracing intersection, ray tracing position fetch, ray tracing reflections, ray tracing shader binding table data, ray tracing shadows. We need to do ray tracing textures and ray tracing textures. So ray tracing textures and ray tracing GLTF, and also again, I'll do ray tracing callable. So there's 3 other things that I have to do, and then we are done with the ray tracing stuff. So I hope you guys enjoyed the ray tracing series. In my opinion, it's probably the most fun stuff, just because, like, you know, you're shooting rays into a scene and like stuff happens. Yeah, I hope you're enjoying this series. I'm gonna try and finish it out as soon as possible and get you know, just get that out of the way. And then we have a whole bunch of other stuff that we got to do, but it's not ray tracing stuff. So, you know, but it is, of course, dealing with Vulkan, right? And all of the things that Vulkan affords us to do. So we got to do it, guys. But we, you know, we made good progress with the ray tracing stuff. Memory operations, yeah, we need to actually double down on the memory stuff. I need to double down on it too. But yeah, we have our RayGen. Notice that there's just a lot more going on with the RayGen stuff. I mean, with the RayGen shader, the mist shader is always very simple for the most part. And then the hit shader is also pretty simple. You're just basically changing the color for whenever you get a hit, right? We have our source code. We now know because of the barycentric coordinates videos that this attribs is what is used for the barycentric coordinates. So when we get a hit, anytime you see a hit shader, you know that there's going to be a hit attribute ext value, you know, somewhere, you know, because we want to get the barycentric coordinates and stuff and blah, blah, blah. And if you want to get the vertex of the triangle that you actually hit, then you got to get that position fetch extension and stuff, right? We don't include it here because we're not using that, you know what I mean? So you guys are slowly but surely learning Vulkan. I'm proud of you. It's time well spent. Tell your friends about this stuff. It is time well spent. If you have a commute where you're on a train or you're on a bus or you're on, you know, somewhere where you're waiting, if you're flying all the time and you have time to yourself, definitely I would suggest just learning Vulkan in your free time. If you're, you know, flying, traveling, whatever, you know what I mean? Learn Vulkan in your free time. There's a lot to learn, guys, as you can see by all of these examples, right? Shout out to the Sascha Willems, the author of this code. It's very impressive and helpful. I believe this is the best set of examples for Vulkan on the internet, right? So the idea is to learn all of this stuff, learn Vulkan, and then you are free to create your own stuff, right? Yeah, but before you can create your stuff, you got to know how this stuff works, right? Tutorial number 1, to install the Vulkan API on a Windows-based machine with a Vulkan-capable GPU. Tutorial number 13, to install all of these examples. If you want a ray tracing, if you want to run the ray tracing examples, you need to make sure your GPU is also ray tracing capable. For NVIDIA, it's RTX cards and later or greater. For for AMD and for Intel, I don't know about which models are ray tracing capable or not. You'll have to do your own research on that. Thank you guys for watching. Have a great day.